about to conspire.
Recording started.
And we're going to talk about the geospatial revolution as coined by our friends at Penn State University. We're going to talk about some obstacles and challenges when teaching GIS. Then we're going to talk about free beer. Sorry, we're not actually going to have free beer, but free beer will enter the discussion. And then I'm feeling a little rebellious today, so we're going to do a live software demonstration on a Macintosh, where we actually install the software before your very eyes, just to show you how easy it is. And then we have an alarm that's going to go off at 2:15 to keep us on schedule. And when the alarm goes off, we will have a raffle and give away some of these maps, which were just released from IMAS Geographics. They're award-winning, and they have thousands of features in them. And it's the entire United States. So hopefully you can enjoy using that either at home or in your classroom. Unfortunately, the maps are not going to be available to our friends online. You do have to be present to win. We appreciate anyone who is joining our session via the internet. My name is Christine Bush, and I work with Ohlone College, and I'm very happy to have Richard Gordigat, who is my colleague, in the room with me for this session today. I'm part of the ICT Pathway Program, and what Richard has invited me to do is to sort of set the table for introducing open source GIS into your curriculum. If you have any questions after this conference is over, I invite you to take down my contact information. I would be happy to talk to you further about consulting with your program, or just answering general questions, or giving you a nudge in the right direction, whatever you might need. That's my phone number. If you can find your way to LinkedIn, I have an account there as well. And you can follow me on Twitter, if we have any Twitter users, via the username webmaps. My background is a bit eclectic. I started in radio. From there I went to art school until 1995 when the internet happened. And from there I spent some time working with XML, Cold Fusion, Flash, and then eventually found my way into Geographic Information Systems, or GIS. That was in about 2003, and I have been working almost exclusively with GIS ever since then. I think it's a really exciting field, and what I'm sort of interested in doing in this session is to offer an alternative to what our keynote speaker recommended this morning, which was to have us as educators start producing T-shaped people. I prefer to be started producing G-shaped people. I think G-shaped people would be more well-rounded students, and might have some other benefits that we'll discuss as we go through the presentation today. But just to make sure that everyone is on the same page initially, I don't know if we have geography teachers in the room, or what this collection of folks here specialize in. But just to get us started, I wanted to play a short video that sort of explains how geographic information systems have evolved. And this is part of the project that I mentioned at Penn State University. It's a project that they've developed just to sort of make the geospatial revolution that you may have been hearing about in terms of Google Maps and other areas sort of come to life for students and educators as well. So I hope you enjoy this.
There's nothing new about maps. You can imagine, without being able to talk, somebody showing where you're going, and draw a line showing the river is, and X where they are now, and X where they're going to go. Viewing the Earth has really been based on technology. The Babylonians etched the lay of the land on clay tablets in 2300 BC. And then in the 15th century, with the advent of printing, they started making maps using wooden blocks.
Surveyors would map by making measurements in front of them to a reference point and back behind to the reference point they had just passed. That information had to be transcribed into a map. From in the air, it's as if we sent out thousands of surveyors all at once. Remotely sensed data provides highly accurate measurements of the Earth and the features on it.
We rely on satellites for pictures of the Earth, for communications, for navigation, for weather. Geospatial technology has become woven throughout the fabric of how we live.
About 50 years ago, people came along and started building on big old mainframes, the Geographic Information Systems, which would integrate a map information about culture, about population, about demographics, about physical environment. GIS allows us to bring it all together. I used the first commercial GPS receiver. It took 2 men to carry it. Our antenna was a meter square piece of aluminum. We had to have it generated for it. Massive batteries. The Census Bureau in the United States needed to capture all of the line work for roads, railroads, hydrography, and then boundaries. That formed the basis of the first Tiger files in the late 1980s and supported the 1990 census. Tiger is an impetus to technological developments like MapQuest, Geography, followed by Google.
Google Earth introduced people to the coolness of the place. I am here, where's the nearest Starbucks, or where's the nearest hospital?
Now we're all carrying around GPS. We've got really rich interfaces that allow us to do things that we would only imagine previously.
On a mobile device, you are the center of the map, and the city is around you. Not you see a city and look for yourself on the map. It's putting you in the map.
So if you would like to enjoy some more videos of that nature, I think they do a fabulous job with the multimedia and the timeline and the animation using satellite imagery that makes some very complex concepts sort of immediately understandable to you in a very short amount of time. And they have a whole series of these. This is where you can find them. For those of you listening on the internet, the URL is geospatialrevolution.tsu.edu. And there are some other resources there that I just wanted to take a moment to share with you that you might have an interest in integrating into your classroom. So this is the Geospatial Revolution website, and you can scroll down, click on the For Educators section. And you can see that they have content prepared for both K through 12 and for post-secondary education. classes. And they also have some information about GPS. GPS is part of Geographic Information Systems. It's the global positioning system, and that is the array of 24 satellites, which are constantly in orbit around the planet. And through triangulation, you can take very detailed measurements of whatever it is that is your topic of study. And that is also the same system that we probably more and more rely on to help us find our way from here to there. Some barriers to entry in introducing GIS into your program should probably be very familiar to you. Of course, teachers are very busy, so time is a problem. Constrained curriculum, what I mean by that is I am an advocate of introducing GIS into all fields of study. I would like to see students be able to go to the library and or just call up their local campus network and get to a server, a geo server, and be able to find or create resources for their research, regardless of what field it is, whether it's English or history, biology, science, of course, geography, geology, and ITC. ITC can make use of GIS, as you'll see when we get to the live demo. There's also a concern, of course, that you have to have a lot of technical skills in order to get this up and running. I'm hoping that in time, perhaps, that an organization like MPIT might take up the banner of GIS to the degree that we have an MPICT geo server, and everyone in the MPICT network can have a central location to store their geo-data. But the technical skills are needed to a degree, but by doing the live demo that we're going to get to shortly, I hope that I can convince you that maybe you could download the software yourself and give it a try and just start exploring with it. It's not so scary. So if you can get past those barriers to entry, there are some challenges in the arena waiting for you. One is stereotyping. For example, we tend to think that GIS is just for geologists or just for programmers or just for scientists, and as we were just discussing, that need not be the case. There's the financial justification, which finding funding sources for GIS programs could be a session unto itself, so we're not going to spend a lot of time on that area in this talk. I would like to move on, however, to the topic of commercial insinuation. And by commercial insinuation, what I mean is that, I don't know if you noticed, but in the Penn State video, which I give them kudos for, all the featured players were the Air Force, the USGS, ESRI, ESRI, who is a very big elephant in the GIS world, Yahoo, Google, Bing. These are all commercial entities. There is no inclusion as yet in the geospatial revolution for open source GIS. So I want to take a few minutes and talk in general about the importance of open source software. And forgive me if this is old hat for some of you, but I think it's important and of interest to discuss. Because the fact is that government and corporate usage and development of GIS, as the video showed, is actually very old news. So what I want to suggest to you is that the real revolution is actually happening in the open source arena. Programs like OpenGeo, OpenLayers, OpenStreetMap, VOGC, these are the tools that are the real game changers, because these are the tools that anybody can use. We want to democratize the creation of geodata. Another concern is that open source GIS is not being taught unto itself necessarily. I think there are certain endemic values to the idea of discussing open source software versus proprietary software and free software, software licensing. And something that ESRI in particular has the ability to do is to come onto a campus or find a foundation and provide them with a large number of licenses to use their software, which is very complex and very difficult to maintain and manage. It's also very expensive once you leave the classroom. And I have several colleagues in my experience who have gone through GIS programs, been trained on very high-end and sophisticated commercial GIS software, but then once they leave the program, those tools are no longer available to them. And we aren't inculcating in students the core underlying principles that make this software work.
On the reverse end, how do students who learn these open source translate into the industry where they're using the ESRI software? Is there any problems because of the different level of?
I don't think so. In fact, I think that industry may well find that students who have been trained up using open source geographic information systems are better employees than students who have learned the sequence of button clicks and installations that you need to do in order to get this more powerful production-oriented software to work, because they have to interact more directly with the components of the GIS system, and we're going to see that very shortly here. That's a very good question. So I just want to set a place at the table for open source GIS, but that's not the place setting I had in mind. It looks more like this, as you'll see. So very quickly on this slide, I just want to do a quick review of some terminology. There is open source, which is easily confused or conflated with open standards, which are about interoperability. Open standards are a good thing. We can go to the OGC and see some of these standards. GML and JPEG 2000, KML, the markup language that Google initially developed for use with Google Maps and Google Earth, is an OGC standard. Sensor models, these are some of the mechanisms that were being discussed in the keynote presentation this morning. There's a very long list here. Simple Features SQL, that's the query language that you use to ask spatial questions of a geodatabase. So we refer to open standards for interoperability, and many of the commercial software products, to their credit, of course, adopt OGC standards. But the fact that they use open standards does not make them open source software. Open source is a mechanism for code transparency. It's a very pragmatic decision that a programming team makes as to whether they want to be an open source project or not. I mean, some of the benefits of an open source project are that you can outsource some of the work to the community. You have more players, you get more feedback, it's a more iterative process. However, there is a further distinction. Free and open software is freedom to code, not free code. And so it's easy to confuse these ideas. And the example that is often given here is free as in freedom, not free as in beer. So that's as close as I could get to free beer for you folks today. So
That's it?
that's it. That was the free beer. I invite you to visit the Free Software
Open
Foundation.
source beer?
Free and open source beer, yeah. The Free Software Foundation is an excellent resource for you to learn about what we call FOSS, free and open source software. And there is a FOSS convention if you want an excuse to go to Denver in September. I'm very tempted by that. OSGeo, however, is really where the rubber is meeting the road in terms of open source GIS. And these are programs that you can find at osgeo.org. And they have a section for the educators, excuse me, floppy click. And these are the projects I'm most excited about, OSGeo projects, like RAS GIS, GeoServer, Map Builder. Map Server is an open source software project from the University of Minnesota. Quantum GIS is a geo IDE, an editor that you can use to create and attribute geospatial data. MapFish is an interesting project. That is a printing module, which is now being included in the OpenGeo Community Edition, which we're about to install. Here we go. So why all the fuss about all this free software and open source software? Well, commercial software can lead to low return on investment financially and educationally, as I was describing earlier. Of course, software changes a lot. That's one of the best things about it, but it's also a burden. And so if you have to spend a lot of money constantly buying the next version of whatever commercial product, and they've changed it, then that gets expensive. But it also is a problem educationally if learning the buttonology, as Allison Mizan-Lincoln at Foothill College refers to it, is the educational product instead of understanding the core concepts. Also, when you introduce commercial software requirements into the curriculum, then you're inviting software piracy, because people will want to be able to do their work at home if they can't get to the lab, and this is well documented. And of course, my friend Lawrence Lessig, who I do not know personally yet. Hi Lawrence, I hope you see this someday. He's now at Harvard, but I highly recommend his book Remix. And the idea behind this book is just about how the generation of students that are coming up now really have very few qualms about pirating software or remixing things up. And we might as well embrace this and find a way to legitimize the activity, or at least acknowledge it, rather than just continuing to turn a blind eye to the fact that software is being pirated. So in order to create these G-shaped students, this is my version of the pyramid of literacy. And my pyramid may not be quite as tall as the one we were looking at this morning, but it is more fundamental. At the bottom, we need to have English literacy first and foremost, then geographic literacy, computer literacy, And then, and only then, can we really start getting into geospatial literacy, which is the idea of working with points, lines, and polygons, and adding tables of attribute data, which are associated with each of those geometric types. And perhaps after a student achieves a certain comfort level with geospatial literacy, then they might be inspired, as I am, to continue their pursuit of mathematical literacy. Okay, so let's do the live demo. Any questions before we go to that?
I just wanted to say, I think it's pretty obvious that this is an ICT conference, and at our school, GIS is taught in our geography department, which is a separate division from computer science. And, there's an obvious convergence. I think everybody here would agree with ICT.
Nobody else wanted it. And we did.
That's good to hear. For those of you listening on the internet who might not have picked that up, someone in the room here is just pointing out that GIS is being taught in their institution through the computer science department, whereas at a learning college it's taught through the geography and environmental studies department. Yes?
I'm from Folsom Lake College. We have GIS under the geology area, sort of geosciences, but there's a lot of collaboration going on with CIS and also with our instructional development and design coordinator to develop iPhone apps related to maps of the campus and things like that that use GIS.
Absolutely. I think
some informal things as well as the formal.
Well, you make an excellent point with the introduction of the emerging mobile platform. That is really a natural area for development, because you more and more frequently have these surf chips, which are the GPS chips, in your smartphones. So I've actually had one teacher come to me because we were working with him on a program, and he tried to do one lab using some older GPS devices, and he found that some of his students were able to actually get better results using their own smartphones than a Garmin GPS device, which I think is pretty telling. So in the interest of time, of course, I have already downloaded the OpenGeo Suite. You can find that at opengeo.org, OPENGEO.org. It's part of the Open Plans initiative, and there is an Enterprise Edition which you can subscribe to, and that comes with full support. There's also a Community Edition which you can download for free. It's fully functional, but it doesn't provide any support, so you might need someone just to help you get it up and running if you find any quirks. I would also like to point out for those on the internet who might not be able to recognize this, we're going to do something which I have never seen done in a presentation, which is to install a Geo product onto an Apple operating system. We're doing this on a Macintosh. There isn't even, there's not an ESRI software product that will run on a Macintosh. So it's just going to step us through the familiar GNU license agreement, the GPL license. We're going to put this onto our hard drive. We can customize it if we don't want to install all of these components, but that's what's about to be installed. Geo servers, extensions, PostGIS, which is a layer that sits on top of PostgreSQL. There's a dashboard client, and of course an uninstaller as well. The OpenGeo Suite is built on Java. It's a Java product. So So you do have to have a Java virtual machine running in your operating system for it to work.
So it won't work on an iPad.
I don't think it will work on an iPad yet.
No Java support.
Yeah.
The password you typed in, that was your Mac password?
Yes, that was the administrator password required just to install the software. So if you're doing that at home, you would need to do that. If you are trying to do this over the network onto a computer lab, then your installation script would need to take that into consideration.
Does this run off the server or individual workstations?
This will run off a server, but this dashboard suite that we just installed is designed for individual use, but it can be installed on the server, and then server accounts can log in and make use of it that way. So we're done. That wasn't too painful. No glitches. So the first thing we do is we start it up by clicking on the Start button. This initializes the Jetty engine, which is sort of what runs everything underneath OpenGeo. Just takes a moment. While that's happening, I can give you a quick tour of this dashboard, which is not required to necessarily run anything. Each of these components, PostGIS, the GeoServer, GeoWebCache, which is a tile creation engine, the GeoEditor, Styler, and Explorer, all of these run in the browser. So when everything gets started and Apache is running and the Java is initialized, then we have access to these core components, and each of them run in the browser. So that is an added benefit. And we're up and running. Take a quick look under Preferences, which is located in the tab on the left-hand side of the window. And you can see here that you have some control over where GeoServer stores the data. GeoServer is a product which allows you to serve data out in different formats. So if you have shape files, for example, you can simply put your shape files anywhere you want, and then set that directory path under your preferences. And then what GeoServer does is it takes those shape files and allows people to download them in different formats. It does on-the-fly conversion for you. And there's a standalone version of GeoServer which actually allows you to download the data in many more formats than this suite does. The suite provides KML and open layers publication of shapefile data, or you can import geodata into a geodatabase, which is PostGIS, which is a layer that runs on top of PostgreSQL, which is really a world-class database. So you have two options as far as sourcing the geodata, shapefiles, or a geodatabase. And then once you get that repository set up, GeoServer allows users to log in and get it in the format that they need, including TIFF or GML or an RSS feed. It's really quite remarkable. The first thing you probably want to do is familiarize yourself with the workflow. So you can just click on Getting Started, and it sort of walks you through the general workflow of a GIS project, which is loading data. There's a component called PG Shape Loader, which provides a wizard, essentially, for loading those shape files into PostGIS. And once you have your repository of information, you serve your data, you can edit, style, you can create a map, print it out, give it to your students, publish it on the internet. They also have a recipe book for things that you can do with the OpenGeo suite. So let's come back to the dashboard and import some shape files. It's a little tricky in this format. Here we go. You can see I've got multiple versions of Shape Loader running now, so we'll quit some of those. I was expecting it to be in the browser, but so this is the GUI that you can use. You can just navigate to wherever you have your shape files. I have some Tiger data from North Carolina, my home state. I downloaded that. And a shape file is an aggregate file format. 6 different files work together to make a shape file. So when you download Tiger data, you get folders within folders that contain shape files based on various feature sets. So let's see if we can find something that'll load pretty quickly for us, not too painful, like counties perhaps. There's a shape file. Say open. We don't need to give it a username. We can test our connection. Out of the box, database connection succeeds. Magic as far as I'm concerned. The SRID is what we use to tell it what the projection of the shape file is. It's a false to negative 1, which means unknown. I believe there's an option in here that will figure that out for us. We're going to use 4326, which is WGS 84. It's the standard world geographic projection used by Google Maps and Google Earth. So we're going to set that to 4326 and say import. Shapefile imported. Okay. Now we have some data we can look at. Let's go to GeoServer. And as you can see, GeoServer runs off a local host on port 8080 by default. And the process we just did was to import those shape files into PostGIS. And now what we're going to do is port or point GeoServer at PostGIS so that we can create some KML or some open layers which will get that data onto the web for you. But before we do that, out-of-the-box GeoServer includes a data set based on municipal data from Medford, Oregon, which is very helpful. It also has some boilerplate data sets, world borders, world cities, just to get you started. And you can see as we scroll over to the right here that we can pick what order we want this to be served up to us in, as Open Layers is a JavaScript framework. Which includes the ability to change the format of the tiles that are being created. You can have PNG or GIF or JPEG. And you can also change the default dimensions of your width and your height as far as what size you want your web map to be. Leave those both at auto. Let me give this one more try. That didn't display for us. GeoServer handles raster data as well as vector data. So vector data are your points, lines, and polygons. Raster data are your aerial photographs, or your data which has a continuum as opposed to sharp edges. Here we go. So this is a raster image. And you can click around on it. And you can see in real time, just like you're used to with Google Earth, getting long and different locations as you move your cursor over it. And as you click, you get attribute data. Let's go back to GeoServer one more time and try, let's take a look at some KML. We'll just save this onto our desktop. Got it. And we can launch Google Earth. Which is always fun. This is the latest Google Earth 6. I just downloaded this last night, so hopefully this will cooperate for us. And then we can stay open. Go to our desktop, find our parks. And zoom in to Medford, Oregon. And there they are. As an overlay with attribute data. So that's one component. I guess we've looked at two now, actually. We've looked at PostGIS, and we've looked at OpenServer. We've created an open layers application.
Does Google have any live now?
No, that's a massive worldwide data set that they maintain. So different parts of Google Earth are more current or up to date than other parts. So it's constantly changing, much like the planet is, but not based on organic mechanisms, but based on availability of the imagery.
When you briefly drill down into Google Earth to the block level, and you go deeper into that what methods is there to convert it so that it doesn't, is there anything, is there additional cost that Google charges so that when you want to get down to the individual level?
Now, the question is, are there any charges based on the level of detail or the zoom level that you're looking at imagery in Google Earth? And no, there are no charges for that. Google only charges licensing fees for commercial usage of Google Earth.
But even in the commercial version, when you get down and drill down to that level, it still blurs no matter what?
Blurs?
Yeah. The image itself blurs?
No, it will not zoom below its native resolution, so you shouldn't have blurring. Now you will find that some tiles are less focused than others. But the way Google Earth works is it has 18 zoom levels, so that are 18 sets of tiles at different levels of scale. And once you get down to that bottom level of scale, then they cleverly sort of solve this problem with innovation. And so they created the Street View. And so now you can click on View Here, Shown, and Explained. How does it? We are just about out of time, so we're going to do our raffle, but I want to...
He's been in the house upstairs, we're going to trade raffle.
Oh, I see what's going on. Here we go. So you get this little icon that you can drag to an intersection, and then it takes you, if photography is available, of actual street view perspective, as if you were walking down the street. I apologize for not picking a very good example here, but if we had more time, I could do a whole other session on just Google Earth. But I hope that I'm sorry?
It'll still be blurry at that level. The focus isn't clear enough at that level. We don't have to take time out.
That's okay. Yeah, I mean, this does look a little blurry right now, just because of the tilt.
You're a fancy car.
But Google has a whole fleet all around the world of these crazy little cars that you might have seen with the 360 cameras mounted on the roof, and they're taking panoramic images and cross-referencing those with location and really doing interesting things.
Any privacy or security infringements as well?
But they can't get.
That is an ongoing debate. The question was whether there are any security and privacy concerns surrounding the imagery in Google Earth. I've been to some presentations and talks about that, and they do go to tremendous lengths to anonymize faces and scrub things out that might be of security interest. So they are making a good faith effort, but it does get some people riled up a bit. So that's an interesting question. I just wanted to wrap up. I'm sorry we didn't have time to get to some of the other features, but I hope I've piqued your interest a little bit in the OpenGeo Community Suite, which is what you can go home and download and play with a bit. We're going to stop the Geo Suite now, close the application, and just to bring things full circle, we'll come in and, while we're doing our raffle, uninstall the software. Because I think there is good apprehension on the part of some folks about trying things out, installing things, but they don't always give you a clean uninstall. The OpenGeo Suite is now uninstalled, and we're finished. So I appreciate your joining us for this session, and we have 4 maps to give away. Where is that map? Let's see. George Thompson.